It is often said that mathematics is a universal language. No matter where we are or who we are, regardless of culture, country, gender, race, or even religion, certain mathematical principles remain true. For example, 100 can always be reduced to its basic building blocks of 2s and 5s, no matter what language it is that we speak every day. Mathematics is indeed a language common to all of us on planet Earth, and the most fundamental letters of its alphabet are called the primes. These numbers have the very unique quality of being divisible by only themselves and 1. They can't be factored any further, and as a result, they're often called the atoms of arithmetic. Prime numbers are so fundamental and mysterious that they've intrigued human mathematicians for thousands of years. Are they so fundamental that other intelligent beings in the universe might know about them too? In the 1960s, SETI suggested that if there are other intelligent beings out there, they might share the language of mathematics with us. SETI relied on the idea that math is so fundamental to how we describe the physical universe that other beings might see the universe through the same lens. And if we shared this common language of mathematics, then the prime numbers, those atoms of arithmetic, might be used as a basis of interstellar communication. In 1974, at the Arecibo radio telescope in Puerto Rico, astronomer Frank Drake beamed a message into outer space. The message consisted of 1,679 binary digits. Drake chose 1679 because it's a semi-prime, the product of two prime numbers, that can only be broken down into 23 and 73. Drake arranged the bits in such a way that when viewed as a rectangle of 73 rows and 23 columns, it would read as a pictogram that included the numbers 1 through 10, the DNA double helix, and the Earth's solar system. On Earth, at least, we use math to explain everything from microscopic DNA to the mysteries of outer space. And while it's a language that might connect us to intelligent life from another galaxy someday in the future, today it certainly connects us to each other across cultures and continents, and even to our ancestors from the past. Now, this is a replica of the Ishango bone, which originated in Central Africa some 20,000 years ago, and it's thought to be one of mankind's first tally sticks, a simple device used for counting. In its use of notches to stand in for objects or instances, it becomes one of the first examples of abstract thinking. But even more, the columns of asymmetrically grouped notches suggest that early humans had a mathematical understanding that went beyond mere counting. The notches on both the left and right columns are all odd numbers, 9, 11, 13, 17, 19, and 21. The numbers on each of those columns add up to 60, and the numbers in the central column add up to 48. Now, 60 and 48 are both multiples of 12, perhaps indicating an understanding of multiplication and division. But perhaps more intriguing is the fact that the numbers on the left column are all primes. 20,000 years ago, someone may have recognized these numbers for their uniqueness. Did early humans know what made the primes special? Now, most historians agree that ancient cultures seem to appreciate numbers for their utility in things like commerce, agriculture, and calendars, but the idea that numbers could be interesting in and of themselves seems to be something that emerged relatively late, some 18,000 years after the Ishango bone, with classical Greek civilization. Scholars like Pythagoras, Aristotle, and Euclid, they were the first pure mathematicians who, beginning around the 7th century BC, began to explore numbers for their own sake. In fact, the word mathematics comes from the Greek mathema, which means learning, and the word calculation is from the Greek calyx, meaning pebble, and from that we get calculus. Some of the Greeks' most complex and abstract explorations began with something as simple and tangible as a handful of pebbles. Any whole number can be represented by a corresponding quantity of pebbles, and one way in which the Greeks classified numbers was according to the shapes that could be produced with their pebble pile equivalents. For example, if a number of pebbles could be arranged in a square, that number was called a square. Thus, with the sides being equal, a number times itself, as we know, is said to be squared. 3 rows of 3 pebbles, 3 times 3 equaling 9. That's not a bad example. So most numbers, even if they couldn't be shaped into squares, could at least be represented by rectangles, where by rectangle we mean only those that have more than one pebble in each dimension. For example, take the number 12. It can be represented by rectangles that are either 2 rows of 6 pebbles or 3 rows of 4 pebbles, so that the height and width of these boxes actually give us a visualization of a basic multiplication problem. Since a rectangle has length and width, the number of its pebbles represents both the rectangle itself and the answer to a multiplication problem, such as 3 times 4. But notice that certain quantities of pebbles just don't fit in a box. If you're trying to make one of these so-called fat rectangles out of a number like 11 or 13, something is always left over. So a number like 11 or 13 can never be the answer to a multiplication problem other than 1 times itself. This ends up being true for many numbers: 2, 3, 5, 7, 11, 13, 17, 19, on and on it goes. Today we call these numbers prime numbers. And like any kind of surprising discovery, be it a strange kind of bird or a flickering star in the sky, once it's identified, it needs to be investigated. So it was Euclid, the man that most of us think of as the father of geometry, who first recorded the properties of the primes. His investigation of the primes begins with what we call the fundamental theorem of arithmetic, and this states that every natural number greater than 1 can be written as a unique product of prime numbers. We call these prime numbers its prime factors. For example, 12 is the product of 4 times 3, and this can be further reduced to the prime factors of 2 times 2 times 3. Likewise, a number like 1200 is the product of 3 times 16 times 25, and this can then be further reduced to 3 times 2 to the 4th power times 5 squared. Thus, the fundamental theorem of arithmetic establishes the importance of prime numbers as the basic building blocks of any positive integer. This is why we call them the atoms of arithmetic. So then, Euclid goes one step further, and that's the point. Having identified the primes, we can now ask questions like, how many of them are there? And what Euclid proved is that there are an infinite number. So let's see how he did it. Euclid's proof of the infinitude of primes shows that if we multiply together any finite collection of primes and then add 1, the resulting sum is not divisible by any of the primes that we start with. For example, multiply the prime numbers 2, 3, and 5, and then add 1. The result is 31, a number which can't be divided by either 2, 3, or 5. But in fact, 31 is itself prime, so we've discovered a new prime number. Now, if we continue down this path and use the primes 2, 3, 5, and 31 to create a new number, this time we get 931, which also cannot be factored by any of the primes we used to create it. As it turns out, 931 is not a prime. It can be divided by both 7 and 19. But guess what? We've just discovered 2 new primes. So even if the output of Euclid's formula is not itself a prime number, any of its factors must be new primes. Now you might notice, however, that Euclid's method doesn't give us prime numbers in the order that we'd expect. In this example, it skipped over the primes 11, 13, and 17. But his method does show us that out of any list of primes that we use to make a number by Euclid's method, there's always another waiting to be found. Consequently, the list of primes must go on forever. There must be an infinitude of prime numbers, each one larger than the next. If we keep repeating Euclid's method, multiplying all the primes that we have at any point and then adding 1 and then looking for new primes, we always end up with these kinds of gaps. 7919 turns out to be the 1000th prime number. And here's a prime that appears much later down the number line. But what about those skipped numbers? Euclid's proof of the infinitude of primes doesn't provide a systematic way of finding all the prime numbers. But 100 years after Euclid, another Greek mathematician, Eratosthenes, tried to find one. Eratosthenes designed a simple algorithm, that is, a set of well-defined instructions or a kind of mathematical recipe that sifts out composite numbers from prime numbers. It came to be called the sieve of Eratosthenes, and here's how it works. Suppose we wanted to find all the primes less than or equal to 100. So beginning with 2, we work our way through the numbers in the following fashion. We keep the first prime that we encounter, 2, and then delete every multiple of 2 in the list. 4, 6, 8, 10, 12, and so on. They all disappear. Then we go back to the beginning of the list. The first number that wasn't deleted is 3, and it's a prime number. And then we work through the list again, this time deleting all the multiples of 3. Then we go back to the beginning, and the first one that we see is 5, also a prime, not divisible by either 2 or 3. So using this process, all but the primes are eliminated, and you have discovered every prime in the list up to 100. But remember, there are an infinite number of primes, and the sieve of Eratosthenes is a pretty tedious and time-consuming way of finding them. Is there a better way? Could there be a formula that produces prime numbers? That's the sort of thing mathematicians love to play with. Are there better ways to do things, formulas to make things, to play with ideas, twist and turn the numbers around, looking for patterns that might lead to an understanding of something as mysterious as the primes? So now the formula for a Mersenne prime is so beautiful, but the numbers grow so quickly that in fact there are hundreds of mathematicians out there these days searching for Mersenne prime numbers. GIMPs, the great internet Mersenne prime search, is a bunch of, well, prime hunters that link together thousands of computers all around the world working to find larger and larger Mersenne primes. But by the year 2006, nearly 4 centuries after Mersenne, only 44 have been found. The 44th Mersenne prime, discovered by 2 mathematicians at the University of Central Missouri, is 2 to the power 32,582,657 minus 1. It has 9,808,358 digits. This is a number even larger than the number of atoms in the universe. And it's in discoveries like this and in the ongoing pursuit of even larger Mersenne primes, or perhaps proving that no such larger primes exist, that we find the joy, the fun, and the beauty of mathematics. It is truly the one pursuit where it makes sense and is perhaps even required to take your explorations out into the infinite, where no one has gone before. And so, mathematics offers the explorer a kind of freedom, bound only by the laws of logic. We can pose our own puzzles, or take on those puzzles posed by the world around us. Whether large or small, each unsolved puzzle or problem is like a new mountain to be scaled, a sea to be crossed, or a new frontier to be explored. Now, there's that 44th Mersenne prime again. It's amazing that although we may have been aware of the primes for 20,000 years, so much about them remains unresolved. Patterns have been observed, but we can't be sure the patterns continue on the number line out into infinity. We found the 44th Mersenne prime, but we don't know if it's the last one or if the pattern goes on forever. What's more, the Mersenne prime is just one kind of pattern we can find. Now, take a look at the first few primes. We see several examples of twin primes, pairs of primes that are just 2 units apart. 3 and 5, 5 and 7, 11 and 13, and now we go farther and farther, 827 and 829, 1607 and 1609, and so on and so on. Maybe.